So our third and final chi-squared test is association. So we started with goodness of fit, in which we were given a distribution and how often each of those things should occur. And so how well did it fit? What was the goodness of fit for each of those categories? Or the homogeneity test, which was from two or more populations, are they the same or not? That's what homogeneity is. And so we looked at two different brands of gummy bears from two different populations. So the final test is also in a two-way table like homogeneity, but it instead comes from one population. So we are looking at Kristen Gilbert, and you can read about her, a highly skilled nurse, late 80s. The issue was, as wonderful as she seems to be in this first paragraph, she had a tendency to be nearby when patients died. And so co-workers dubbed her the angel of death. And so Prosecutor Welch thought that this was significant, and other people grew suspicious. And so after a concern from this particular time period, criminal investigation, an affidavit, and we started to look at whether or not this really would be a coincidence or could this have happened, because there is in fact an association between whether or not she was present and whether or not people had passed away. So some explanations as to why she might have more deaths on her shifts. Perhaps it tends to do with the hours of her shift. Maybe patients have a tendency to die in their sleep. And so the shifts that are overnight, those nurses tend to see more patients pass throughout the night because it's while they're sleeping. Or maybe she was working with conditions that were in the ICU. And so they were already in a difficult place. And so the condition had something to do with it. And then we questioned whether or not she was capable of the work. And so was she really as good as we thought? What might have happened? And so other statistical evidence we wanted to know, how many different codes, and then causes of death for these individuals, again, kind of related to condition, how many deaths happened when other people were working. Did that have anything to do with it? So the analysis of many 8-hour shifts, 1,641 was presented, and we're looking to see if there's an association. So to explain all of these parts, we have the observed counts typed. So when she was present, 40 people died during her shift. And when she was not present, 34 died for the 74 that died in this particular case table. So we're going to use a chi-squared association independence test. It is one particular sample, and we have two questions being asked. So those are our two variables, whether she was there or not and whether or not they died. So our state plan do conclude. The wording for the null hypothesis is super easy. There was no association between the patient death and whether or not she was present. We could also say that they're independent. And so her presence and the death during shift were independent. But I tend to stick with what we've done all year long, writing the null hypothesis as no difference. And so no association just simply follows that wording. For the alternative, I tend to cheat a little bit and not restate the context there, but instead of no association, we say, yes, in fact, there is one. So checking our conditions. Random was not met. They gathered all of the data that they could. Independence could meet the 10% rule, but it's kind of difficult to assume in these circumstances. So again, what is new is the large sample size, or the large counts, as shown in the table above. So all of my expected counts have to be greater than or equal to 5. So again, my row total times my column total divided by my table total. So if on the calculator you put the 4 observed counts into matrix A in a 2x2 matrix, and then went to stat test and ran the chi-squared test, it again is one of the only ones that it's asking you for your input under the observed, and that's where we put matrix A. The output is what the expected line is for, and that's telling you the calculator will put them into matrix B. So you don't have to clear matrix B from a previous problem. Whatever you run the test, it's just going to overwrite whatever is in matrix B and put those expected counts in. So we had no issue meeting that each of them were 5 here. But again, thinking in terms of that formula and how it breaks down, we had many more people stay alive during the shift, so they're under the no column. And so weighting those counts basically is what happens when we look at row total divided by the table total that tells us each, and then multiplied by column total. So whichever way you think marginally, and then you're multiplying by that other dimension, whether it's the row or column, is where those expected counts come from. And it's a 2x2 table. So if we had the totals all listed here, if we had the row totals listed and the column totals listed, we could fudge one number and put it into the table, and then the other 3 have to fit in order to make those totals work. So if we take rows minus 1 times columns minus 1, that only leaves us with 1. And so whenever we, again, run that on the calculator, we can see these expected counts. We have a ridiculously high test statistic at 86.481, really, really far away. And a p-value so small that it's times 10 to the negative 20th. And so our conclusion here says we have very strong evidence to reject the null hypothesis at any significance level. So assuming there is no association between patient deaths and Gilbert being present, there is essentially a 0% chance of data like this. So again, making a decision in the first sentence and linking it to a significance level, and then interpreting the p-value in the context for the second. So a follow-up question here was, do you think that she did it? And so we looked at conditional probabilities and said, if we know that she is present, 40 of those patients passed away. So 40 out of that row total was 15.6%. If she's not, what happens? At that point, the death rate dropped to only 2.5%. So it looked awfully suspicious whenever she was around. So again, of our 3 chi-squared tests, it is a challenge. We have to identify which one we're using, and it does show up in the wording of the question and in the hypotheses. Hypotheses we tend to just write in words because we're dealing with categorical data here. She did or she didn't, and so symbols get to be a bit of a challenge. My conditions, similar to what we had before, random, independent, and then that large counts or large sample size, which again deals just with expected counts. It has nothing to do with the observed counts. My test statistic, exactly the same for all 3 tests, observed minus expected squared over expected for each of them, and I add them together. So again, because it's organized in a 2-way table, top left and bottom right to just show the span of the entire thing. I had my p-value listed here. My degrees of freedom were up above by the table, but that should be included in the do step. And then the conclusion is the conclusion always is. And so having all of those components in context is important as ever. So as a quick follow-up to this, she was in fact convicted on 3 counts of first-degree murder and 1 count of second-degree murder, 2 counts of attempted murder. You can Google her name and figure out what she did. You can watch the movie if you would like that is about this. She is currently incarcerated and is life sentence without the possibility of parole. So again, not the best, or maybe I should say the most fun way to use stats in the real world in an unfortunate circumstance like this, but certainly shows how it applies to lots of different scenarios.